Right, we're up to the notes of our very first part of our topic of physical quantities and units. All right, we've already discussed in class the idea that a physical quantity consists of both a numerical magnitude, in other words, a number, and a unit. So, for example, 10 meters, a number and a unit. 1.7 amps, a number and a unit. So you could think of your own examples there. There are obviously an infinite number of possibilities of physical quantities that could be expressed that way. All right, the SI system, System International, there are 7 what we know as base units in the SI system, but as far as the AS course is concerned, we just use 5 of those, and you can get those base units from the learning outcomes. Just to give you the first one, it's going to be length as the physical quantity, the thing that you actually physically measure. The unit that it's measured in is the meter, and then the symbol that we use for the unit is little m. So I want you to fill in that table with the rest of those physical quantities. Now, once we've got the base units all sorted out, then there are lots of other possible units that we can determine in terms of those base units. And we usually work those out by looking at the formula. Now, don't worry if you're not familiar with all of these formulas at this stage. We'll deal with some of them as we progress through the course. So velocity or speed, perhaps, distance over time. So a simple one. So the derived unit is meters per second. Meters, base unit, seconds, base unit. Frequency. Frequency is 1 divided by the period being the time for one complete oscillation. So the units are going to be seconds to the negative 1, 1 divided by time. Density, Greek letter rho for density. Density equals mass divided by volume. Mass in kilograms, volume in meters cubed, and since it's divided by, therefore it's -3. Again, kilograms and meters are base units. So we've expressed the units of density as a derived unit in terms of those 5 or 2 of the 5 base units. Force, the basic equation for force, mass times acceleration. So mass, kg, acceleration, meters per second squared. 3 base units used, that's the derived unit. Energy, well, energy transfer is the same as work done, and work equals force times distance. So we can take our base units or our derived units here for force and multiply by meters to correspond to distance. So kg, meters, multiply again by meters for the distance, so it becomes meters squared, seconds to the -2. Power is work done divided by time taken. So we take the derived unit or the base units for energy and we divide by seconds. So kg meters squared, seconds to the -2 divided by seconds becomes seconds to the -3. Be careful with that one. Now, in some of these cases, we don't leave it there. That's the derived units expressed in terms of base units. But because some of those are pretty much a bit of a painful mouthful there, we don't leave it like that. We give it a new name for power. We represent that with capital W standing for the watt. Energy, capital J standing for the joule. Force, capital N standing for the for newtons. Back over the page. Frequency, instead of writing it as seconds to the -1, we write that as capital H little z, hertz. All right, so just be careful though, if you're asked to express things in terms of base units, then you'll express them in terms of these sorts of things here rather than giving the new name there. Okay, all very academic, what we've done so far. You think, well, what on earth would be the use of that? Why would you even bother? And to some extent, I can understand you asking that type of a question. One of the uses of base units is to check what is known as the homogeneity, or you could say the consistency of a particular formula. So we've got a formula listed here, but it's not correct. Now, rather than just blindly using a formula, if you have some understanding of base units and homogeneity, you can see that it's not going to be correct. Little v stands for velocity, measured in meters per second. Little u stands for another velocity, initial velocity, again, measured in meters per second. So if the first two quantities are measured in meters per second, the third quantity has to also be measured in meters per second. That's what homogeneity means. Every term in an equation has to have the same base units. So if we work out the base units of AT squared, A is acceleration, meters per second squared. If we then multiply by t squared, units second squared, we see that the seconds cancel each other out and we'll end up with meters. You cannot have this term having units of meters when the other two are meters per second. So the correct term must be A times T, because if we take meters per second squared and we multiply by seconds, we get meters per second, which agrees with the other terms there. So as you work through the first of the sheets on the assignment, you'll find that there are some chances just to practice this idea of looking at the homogeneity of an equation and figuring out from that homogeneity what units must apply in certain circumstances.